Diffraction is one of the most important properties of light. It causes light to spread as it propagates, like this transverse profile of the Gaussian beam on the left. However, there are classes of light whose beams do not diffract with propagation. An example is a Bessel beam. On the right, there is a transverse profile of a zeroth order Bessel beam that maintains the intensity and the size of the central spot during propagation. In addition, this beam is self-healing, which means that it can experience a partial obstruction by an obstacle and reconstruct itself. This diffraction-free, self-healing beam solves the problem of the limited longitudinal range of the Gaussian beam and is used in many applications including optical imaging, optical manipulation, and manufacturing. What makes the Bessel beams even more interesting is a recent development of techniques to structure the beams. The degrees of freedom of the beam, such as a beam intensity, state of polarization, orbital angular momentum, and wavelength, can be designed to take certain values at the desired points along propagation. This video will introduce some examples of engineering the orbital angular momentum of light. The structured light is a result of superposition of the Bessel beams. This equation is for the rotating intensity pattern that consists of multiple modes of orbital angular momentum, each of which is composed of superposed Bessel beams with different transverse and longitudinal wave numbers. Each Bessel beam in the superposition has a complex weighting determined by the weighting vector A. Here is an experimental setup to generate the desired waveforms. The calculated waveform is converted into a two-dimensional transverse computer-generated hologram and gets mapped onto a spatial light modulator, SLM, which encodes the desired pattern. The generated light then goes through the 4F system, filtered and imaged by a CCD camera over a certain propagation distance. This video shows the central spot of the beam that rotates in counterclockwise direction, and then being switched off from 40 to 55 cm of propagation, and reappearing, rotating in the clockwise manner. Now, let's replay this video to observe what happens. First, there is counterclockwise beam central spot, which is a superposition of zeroth order Bessel beam with topological charge of 0, and first order Bessel beam with -1 charge. Then, the beam is switched off by assigning 0 weighting to each function. Lastly, the beam of superposition of Bessel beams with topological charge 0 and 1 now rotates in opposite directions about the propagation axis. While the resulting beam we see changes the rotating direction, the momentum is conserved in each Bessel beam, carrying a fixed topological charge over propagation. The reversal of rotating direction is also observed in this video. The 4 petals, in place of the central spot, rotate in a counterclockwise direction from 5 to 35 cm. And then, the rotation is in clockwise manner from 35 to 75 cm. And then, it's changed again back to counterclockwise direction from 75 to 90 cm. The number of petals is a sum of absolute values of topological charges of the superpositioned beams. Because the number of petals in the pattern is simply another consequence of the topological charges of the beams in superposition, there can be more or less petals over propagation. This video shows the central pattern evolving from having 3 petals to 5, and after carrying 0 intensity, where the central spot is switched off, to 7 petals rotating in clockwise direction. By being able to design the orbital angular momentum, which has the unbounded value of momentum of LH bar for a photon, the beams find themselves even more useful in various optical applications. For example, the unbounded number of orbital angular momentum states that we can realize is a great advantage in data communications, where each state may carry different information. Used together with engineering of other degrees of freedom of light, this technique opens up so many possibilities. Here are some papers that this video has reference to. and some more papers that you may find interesting. Thank you for watching.